Okay, let's now talk about sequences that seem to have some patterns and structure to them. And in this stage, we're going to play the game that whenever we see a pattern, we're just going to believe it. We'll trust patterns. So watch out for the warning at the end of this lecture. Patterns can be dangerous. Nonetheless, for now, we're just going to believe in patterns and go with it. For example, here's a sequence. 2, 5, 8, 11, 14, 17. And I'm going to ask us to predict, make a good intelligent guess for the next number in that sequence. And I'm sure you're already thinking 20. Because what were you thinking? You probably noticed from 2 to 5, that's up by 3. From 5 to 8, it's up by 3. Up by 3. Difference of 3, difference of 3. Looks like there's a difference of 3 all the way along. In which case, I'm going to trust this pattern of 3s here. I bet the next thing is also a difference of 3. And if I make that guess, that means the next number is indeed 17 plus another 3, 20. Great. So in this sequence, we trusted that the first differences were all constant and it allowed us to make a prediction. Beautiful. Now, of course, as we saw last lecture, not all sequences have first constant differences. They might actually have constant differences down the road. For example, consider this sequence. 2, 3, 6, 11, 18, 27, 38, and let's make a prediction after that one. Okay, so if there's structure, if there's pattern to this sequence, it seems less obvious now. But you might go ahead and do the same thing. Let's look at the first differences. A difference of 1, a difference of 3, a difference of 5, a difference of 7, a difference of 9, a difference of 11. No, I don't see a pattern yet. I don't see a pattern myself. Of course, if I'm slow, I can actually do the differences again, and I get a difference of 2, a difference of 2, difference of 2, difference of 2, difference of 2. Now, surely I see a pattern now, in which case I'm going to predict the next is a difference of 2. In which case the next number after 1, 3, 5, 7, 9, 11 is another difference of 2, must be 13, in which case I predict the next number is going to be, what, 51? Is that right? But here we had constant double differences. So constant first differences, constant second differences. You can probably construct a sequence of constant third differences and so on. In fact, some sequences can just be constant to begin with. No differences needed. For example, 17, 17, 17, 17, 17, and so on is a constant sequence. But here's the thing. As soon as we discover a row of constant differences, we can now actually work our way and make predictions about the next numbers in the sequence, which is great. So there's a lot of structure and pattern here. If you choose to believe the patterns, those beliefs can be very powerful for making predictions. All right, but I want to actually try to capture that and get some real mathematics to it, not only just predict which numbers are next. Can we actually get a formula for the sequences of numbers we're seeing? Because that's what Galileo must be doing. He was in a situation with constant double differences that said, there must be a formula, and the formula is this. How do you do that? All right, so let me look at this more interesting one right here. Let me erase these guys. So we won't bother with constant sequence. We won't bother with first differences constant. Let's play with this one for a moment. And let me do this. If I really wanted to, I could keep taking differences. For example, the third differences are not very interesting, but it's difference of 0, difference of 0, 0, 0, 0, 0. Keeps going, soon it all keeps going. Then I can do the fourth differences, 0, 0, 0, 0, 0, and 0, 0, 0, 0. So I can do an entire difference table, a whole table of all these differences that goes on forever. But here's the thing. Mathematicians started noticing that actually all the key information about the sequence, in fact the entire difference table, lies in the front numbers. Let's call this the leading diagonal. The leading diagonal. These are the numbers that lead each row. So the diagonal row that leads every row. All right, the leading diagonal. Because if you know the leading diagonal of a sequence, then you know everything about that sequence. Let me show you what I mean by that. I will give us a leading diagonal. So it starts with 1, then say blank, 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 blank. And then say it's 3, blank, 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 blank. And that's 0, blank, 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 blank. And that's 5, blank, 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 blank. And that's 7, blank, 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 blank. And that's 1, blank, 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 blank. And then it's 2, blank, blank, blank. I'll give us that leading diagonal. Do you know what? We can now fill in the entire table. Can you see how? Can you see how that actually gives me information about everything? Well, yeah. For example, I can see right now, from 1 to here must be a difference of 3, so that must be the number 4. Great. Now how can I get that number? I don't know, but I can see to get from here, from 3 to that number, must be a difference of 0, so that must be a 3. In which case, to go from 4 to here must be a difference of 3, that must be a 7. Aha! To get to this number, I guess I have to go all the way down here. To go from here to here, there's a difference of 5, so that must be 0 plus 5, 5. To get from here to here must be a difference of 5, so it must be 3 plus 5 is 8. And to get from here to here, I must go up by a difference of 8, that must be a 15. And you can see I can start to build in the whole table now, which is just amazing. 25, 40, and so on. So actually, to know the leading diagonal is to know everything. To know everything. So what I'd like to do now is start with some very basic formulas, because obviously Galileo did something with t squared and t's and 1s. I want to understand some basic formulas. Let's see if we get to know their leading diagonals, see what their leading diagonals are like, and see if we can then use those to find formulas for other sequences based on those leading diagonals. Okay, it's a bit weird, a bit strange, but let's do it. But I need to clean the board, so I'll be right back. Alright, so our job now is to get to know some famous leading diagonals. So let me do this. Let me start with a very simple formula for sequence. It's the formula of nothing but ones. I'll call it the 1 sequence because it goes 1, 1, 1, 1, 1, 1 forever. So it's the constant sequence of 1s. Now if I draw the difference table here, difference of 0, 0, 0, 0, 0 forever. Where the difference of 0 and 0 and 0 and 0, all those zeros have differences of zeros. And all those zeros have differences of zeros, and so on. I'll be here for a while, and I can see the leading diagonal for the constant sequence of 1s is 1, 0, 0, 0, 0, 0, 0, 0 forever. Okay, not too bad. Perhaps the next most interesting formula to play with, standard one, would be like n, the counting numbers. The nth term of the sequence is the nth number. The first term is the first number. The second term is the second number. The third term is the third number. 4, 5, 6, 7. Whoops. Let me do this in yellow so you can actually see it better, because I don't think pink shows up too well. First number is 1, second number is 2, third number is 3, 4, 5, 6, and so on. Alright, so what does its difference table look like? Well, a difference of 1, a difference of 1, a difference of 1, difference of 1, difference of 1 forever. The difference of 0, difference of 0, difference of 0, difference of 0 forever. The difference of 0, 0, 0 forever. 0, 0, 0 forever. Bingo. So the leading diagonal of the counting numbers given by the formula n, the nth number is the nth number, is 1, 1, 0, 0, 0, 0, 0 forever. All right, okay, so we did the constant ones, we did just the counting numbers. Let's now do the formula n squared, the square numbers. So the nth number is the nth square number. So n squared, let me do this, there's going to be room for me, n squared. So the first one is 1 squared, the second one is 2 squared, the third one is 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, and so on and so on and so on. So what does its leading diagonal look like? Well, I guess let's see. 4 to 1, that's a difference of 3. 9 to 5, that's a 4. It's a difference of 5. Difference of 7. Difference of 11. Difference of difference of 9. That's a difference of 11. Difference of 13, and so on. All right, 3, 5, 7. Let's do the next. Let's do the double differences. Difference of 2. 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 Difference of 0. Difference of 0. Okay, life is now good. All these zeros everywhere. Zeros everywhere. The leading diagonal for the square numbers, the sequence of the square numbers, is 1, 3, 2, 0, 0, 0, 0, 0, 0, 0, 0. Great. How high do you want to go? Should we do the cubes? Yeah, let's do the cubes. All right, do the cubes. So the nth number in this sequence is n cubed. So 1 cubed, 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed, 343, and so on. Goodness, this is a big one. All right, let's try to do it. So now this is going to test my arithmetic skills, and you can guess my arithmetic skills aren't the best. Up by 7, up by 19, up by, it was like 37 or something, up by 65, up by, oh goodness, 75, 81, 91, and so on. Up by 12, up by 10, 1, up by 18, up by, oh my goodness, up by, well, that's wrong. That's 61, isn't it? 60, yes, because I say this is going to be 30, this is going to be 24, and this is up, oh, yes, that must be 61. Oh, that's good, because that must be 6, 6, 6. I'm seeing structure. I'm excited by structure. I'm believing in patterns right now. I'm going to always believe in patterns, and I can see I get the sequence 1, 7, 12, 6, 0, 0, 0, 0, 0 thereafter. All right, so there. Now, if you want to, feel free. You'll be much better at arithmetic than I am. What's the leading diagonal for the fourth powers? And if you want to, do the fifth powers as well. But I'll stick with these ones. I won't go too complicated today, but here's some basic leading diagonals, some very basic formulas. The formula of nothing but ones, the formula of the counting numbers n, the formula of the square numbers n squared, the cube numbers n cubed. So we're going to work with these famous leading diagonals. But to do some work, I need more space, so let me clean the board, and I'll write on the side what these diagonals are, so we'll have it on record, and we'll use them for the rest of the lecture. But see you in a moment, after I clean the board. Okay, so here are our famous leading diagonals. Now let's start playing with them. Now let me look at the sequence given by n squared plus n. So what I mean by that is the nth term of the sequence will be the nth square number plus the nth number. So when n is 1, I'll get 1 squared plus 1, 2. When n is 2, I get 2 squared plus 2, 6. n equals 3 is 9 plus 3, 12. n equals 4 is 16 plus 4, 20. 25 plus 5 makes the next one. 25 plus 5, 30, sorry. Silly me. Can't do arithmetic. 6 squared plus 6 is 42. 7 squared plus 7 is 42. It's 49 plus 7 is 56, and so on. All right, grand. So I know the formula for this sequence. But I'm wondering, if I took if all I've done is taken the n squared and I've added the n's, I've taken like these two basic formulas, I'm wondering if the leading diagonal of this particular sequence now is actually a very basic combination of those two leading diagonals. Can I see as a combination of those two? Well, let's try it, let's find out. So, let me look at the differences. It goes up by 4, up by 6, up by 8, up by 10, up by 12, up by 14. I guess my arithmetic was good because that's beautifully consistent. So I'm trusting patterns. Up by 2, 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 up by 0, up by 0, up by 0, up by 0, by 0, and so on, and so on. So there is the leading diagonal. It's 2, 4, 2, 0, 0. All right. 2, 4, 2, 0, 0. I know the answer. It's got something to do with n squared and something to do with n. So it should be something to do with these two right here. So I've got what? Let's do it. So n squared is 132, 132, 0, 0 forever. And n is 1, 1, and then 0 is forever. 1, 1, then 0, 0, 0, and so on. And I want that to equal 2, 4, 2, 0, 0 forever in some sense. So, I mean, what do I mean by equals? So what does equals mean here? So that's n squared. That's n. Oh, look at it, look at it. If I look at each row, 1 plus 1 is 2, 3 plus 1 is 4, 2 plus nothing is 2, 0 plus 0 is 0, 0 plus 0 plus 0, 0 plus 0. So actually it is like adding these two, but I've added them by each row. All the rows add together, and I see this really wants to be n squared plus n. This really is the leading diagonal of n squared plus n. Okay. Okay, this has got me excited because I now have a strategy. Suppose I didn't know what that formula was. Actually, I can't see it, but you can probably see it behind my hand still. Suppose I always given that sequence. Then my job is to find out what the leading diagonal is, and if I could see my leading diagonal as a combination of these basic ones, then that will give me a potential formula. For what that sequence is. Now I haven't said we've proved anything that's going to work, but at least I've got a candidate formula. And then I can actually test my formula. Does it actually work for the numbers I'm given? And if it does work, then I've got a formula that works for the numbers that are given. That would be brilliant. So what I need to do now is give another example where we don't know what the formula is and see if we can deduce what it's going to be and see if we're correct. So we're really trusting patterns here. This is big faith in patterns. And I keep alluding to a warning at the end of this lecture about that faith, but for now, let's go with it. So let me clean the board and give us a sequence for which we do not know what the formula is for it. Back in a moment. Okay, here's now a challenge. Here's a sequence. It's only a finite set of numbers. We don't know what's really going on after the dot, dot, dot. But can we find a formula that seems to fit at least those 6 numbers? Here goes. Our approach is figure out its leading diagonal. The leading diagonal tells us everything. So up by 5, up by, oh gosh, that's 9, up by 13, up by 17, up by 21, and who knows if everybody keeps going. I'm believing in patterns though. Up by 4, up by 4, up by 4, up by 4, up by 0, up by 0, 0, 0, 0, 0, 0, 0. Bingo. So there's the leading diagonal. So my challenge now is, can I recognize that leading diagonal as a combination of these ones? So let me be a little tedious. Let me rewrite them again. So we've got 1, 0, 0, 0, 0. We'll do the first 5. 1, 1, 0, 0, 0. 1, 3, 2, 0, 0. 1, 7, 12, 6, 0, and so on. And I want that to all equal some sense 1, 5, 4, 0, 0, and so on. So there's the ones, there's the n's, there's the n squareds, there's the n cubes. Somehow meant to equal what I've got. And just to keep track of it, the ones, the n's, the n squareds, and the n cubes. So, is this thing here, our leading diagonal, some obvious combination of these ones? Now, I'm a mathematician, I do not like hard work, so I'm going to go to the best I can at the place that has the least amount of work to it. Zeros. Zeros are great. I can see the bottom line is great. A combination of 0 and 0 and 0 and 0 is going to be 0. So whatever I do, I know that 0 is correct, and all the ones below are correct. So I'm going to go for the easy stuff first. Then look at the next number. I want a 0 here. I've got 0 and a 0 and a 0 and a 6. So some combination of 0, 0, 0 and 6 meant to equal 0. That tells me I don't want any n cubes. I don't want to use n cubes, because if I use any n cubes, I get a non-zero number there. So don't use n cubes. I want 0 of these. 0 n cubes. Don't have that one. All right. In which case, if I'm not using n cubes at all, any combination of zeros would just be 0 and I'll be fine. Let's go to the 4. I like the 4 because I'm not using this n cubed at all, so all it's going to be is a combination of 0, 0, and 2's. So some combination of 0, 0, and 2's is meant to give me 4. Well, that tells me I need 2 of these ones. I need 2 of those ones there. None of those and 2 of these, because then I'll have some zeros, and 2 2's makes 4, and I'll be good. I'm not using the n cubes at all. All right, so I'm working my way up because I like the zeros in all this place. The zeros make my life easier. All right, now what have I got? I want 5. On the second row, I've got some zeros, some ones. I've got 2 3's. I've got 6 right now and 0 7's. Right now I've got 6, but I want 5 because I've got those 2 3's. I want 5, which tells me I want negative 1 of these, negative 1 of those, negative 1 of them. Because then I'll have some zeros, negative 1, 1, negative 1, plus 2 3's, 6. So negative 1 and 3, 6 makes 5, and I'll be good. Great. So I want none of those, 2 of those, negative 1 of those, and I need the top number to match still. A little bit more work. So right now I've got some ones. I've got negative 1 plus 2 and nothing. Negative 1 plus 2 and nothing. That makes 1. Oh, I've already got what I need. I've got what I need. So I need 0 of those. I don't need any of those. So what I do need is 2 n squareds and negative 1 n's. My candidate formula, it's still a guess because all I'm doing is believing in patterns and I haven't proven a thing if this is meant to actually work. But at least I've got a really good guess for a formula for those numbers now. Now the question is it actually working? If I put n equals 1, I'll get 2, 1 minus 1, 1, I'll get 1. Put n equals 2, 2 times 4 is 8, minus 2 is 6. Put n equals 3, 2 times 9, 18, minus 3 is 15. 1, 2, 3, 4, 5, 6. Let's go to the sixth one, because I should check all of them, but the sixth one. 72 take away 6 is 66. In fact, you can check it works for all 6 examples. Therefore, that is a formula that's working for those 6 examples. Wow, I love this game. So if someone gives you a sequence, and you can identify some constant differences eventually, and then you can look at the leading diagonal and work out a combination of those things that match it, then you've got a formula that could possibly work for that sequence, and then you can check it to see if it really does work. This is fabulous. This is absolutely fabulous. So let me give you one more example to do on your own, and then check the text under this video for even more examples to practice on. I've got lots of examples for you to try, because this is really kind of cool. This is cool. You can actually get formulas for sequences. All right, so let me clean the board, give you one example, and then I'm going to give you my warning. Back in a moment. Okay, so here's my example for you. 2, 2, 4, 8, 14, 22, 32, and presumably it goes on. Can you find me a formula that actually fits that set of numbers? It'll be grand. It's a lot of fun. In fact, if it helps you out, I'll give you the formula. So pretend you don't know, but it's going to be n squared, so it's going to be one of these, minus 3n, minus 3 of those, plus 4 copies of those. So see if you can get that answer from that sequence, and check it really does work for all 7 numbers. Grand. And then of course for more practice, try the problems in the text below this video, because there's really is fun stuff. It's actually amazing you can get formulas for these sequences. Just love it. Okay, now it's time for my serious warning. patterns. Can you trust patterns? Well, here's my favorite example that puts that into question. So here's some circles. On the first circle, I'll draw 1 dot on the boundary. On the second circle, I'll just draw 2 dots on the boundary. Kind of random. Third circle, 3 dots on the boundary. Fourth circle, 4 dots. 3, 4, if my pink is showing up well enough. 5 dots on the fifth circle, and so on. And sixth circle, seventh circle, and the rest. And what I'm going to ask us to do is just, for each circle, connect every pair of dots with a straight line. Alright, so for the 1 dot circle here, that isn't a pair of circles, nothing to do. But for this second circle, there's 2 dots, I can draw a line between them, great. For the third circle with 3 dots, that pair has a line, that pair has a line, that pair has a line. This one, a line, a line, a line, a line, a line, a line. Okay, it should be neat. I don't want to get sloppy with my edges there, but hopefully that's still clear enough. 5 is going to be a little more complicated. So there's a pair, 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 there's a pair. I kind of seem to be doing it randomly, but notice each dot should be connected to 4 other dots. So I've got 4 there. 1, 2, 3. I'm missing this one. 4. 1, 2, 3, 4. And 1, 2, 3, 4. And that now must be complete. And you can see the pictures get very complicated very quickly, so I'll stop there for now. But clearly I wasn't about to do that one as well because I drew it on the board. So here's my question. Here's my question. How many pieces are there? Well, this has 1 piece, clearly, 1 piece. This has 1, 2, 2 pieces. So there's 1, 2, 3, 4, 4 pieces. The next one has 1, 2, 3, 4, 5, 6, 7, 8 pieces. 1, 2, 4, 8. Any predictions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 pieces. It looks like they're doubling. It's like the powers of 2, the doubling numbers. So in which case, if I did have the patience, and guess what? I had the patience to do the 6 dot example, you would predict how many pieces? Well, I guess if you predict double again, 32 pieces. So I'm actually going to do it. I'm going to try to be neat. We'll see how it goes. All right, so each dot should be connected to 5 other dots. I'm going to make sure there's a line to each of 5 other dots from each individual dot. So this dot is now done. I don't want to introduce any random regions by being very bad drawing, so I'll try to be as neat as possible. So 1, 2, 3, 4, 5. 1, 2, 3. Ooh, I think I'm okay there. 4, 5. 1, 2, 3. I want to go over here. 4, 5. 1, 2, 3, 4, 5. So we're predicting 32 pieces. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 30. 1. 31. 1. Where's the other piece? Here's the thing. It's not 32. It's 31. It's 31. If you drew 7 dots on a circle, can you guess what it's going to be? That you maybe should do it. What's the next number? My point is, you cannot actually trust patterns. And in fact, the next lecture is going to show you what you can really do to mess with people's minds, include your own mind, by making any formula fit any pattern you think should be the case. Crazy, crazy stuff. So mathematicians actually do love patterns. They do love structure. They're motivated by it. They're excited by patterns and structure. But what they really want in the end is a reason why that pattern should be true, because they know that patterns can seem to exist for a while and then surprise us and break down. So they want the logical reasons behind patterns and structure. So yes, mathematicians of course love patterns, but they want the logic behind it, because they know if there's no logic behind it, things can go astray, which is actually very exciting. All right, so I'll see you next lecture to play with what to do if you don't trust patterns. See you then.